We're in Unit 3, Block 4, and we're considering example 2. It says we have a profit function, this third-degree polynomial, p of x. It gives profit in thousands of dollars. X is the number of items sold in thousands. So it asks us to identify local max, local min, and inflection points. We're going to sketch a graph, and then we're going to answer some questions. So first, we are going to identify local max and local min. Remember, to do that, we first need to find all critical points. As I walk through the step-by-step process of finding critical points and finding local max and min, I'm going to be explaining myself, showing my work, explaining the process of how calculus is used to identify these points. To find critical points, we need to find the derivative and identify where the derivative is equal to 0 or where the derivative is undefined. So the derivative of this function, p prime of x, will be negative 15x squared plus 50x minus 4. This is a second-degree polynomial, so it is defined for all x's. There are no undefined p prime values. So I can now focus my attention on finding critical points of the variety p prime of x equals 0. I set my derivative equal to 0. I'm going to use the quadratic formula to solve this. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. I'm going to use the calculator to help me identify the value of the discriminant, the value underneath the radical. So I pop it in the calculator and I find that the number underneath the square root, the discriminant value, is 2260. And so now I'm going to just break this down into approximate values. Again, you can use Excel or you can use the calculator to find these. I find the two x values, two solutions to that equation. At this point, I definitely want to write a sentence to explain what I have now determined. We were finding critical points. I set the derivative equal to 0. I found these two answers. This tells me that p of x has two critical points. P prime of x equals 0 at these two x values. That tells me p of x flattens for an instant at x equals 0.082 and at x equals 3.251, and these are the only places where p of x flattens. Furthermore, we know that these critical points are potential maximum or minimum points. The next step would be to use the first derivative test to determine whether or not each of these critical points is a maximum, a local maximum, or a local minimum, or neither. So we draw our number line. We put our critical points clearly labeled in order on the number line. So we first have the 0.082, then we have the x equals 3.251. We have broken our real number line, the entire domain, down into 3 intervals. I'm going to make notes about what's going on with p prime and what's telling us about p at each interval and also at these critical points. So I'm going to start with the critical points. At the critical points, p prime equals 0, so p is flat. Again, at this other critical point, p prime is 0, so p is flat. We now want to test the 3 intervals. Testing is occurring in the p prime function. Pick a value down here to the left of x equals 0.082. So for example, x equals 0. I'm going to plug x equals 0 into p prime, and I'm going to evaluate it. And if you plug 0 into p prime, you'll get negative 4. I don't care that it is negative 4. What I care about is that p prime is negative. The derivative is negative on this entire interval to the left of x equals 0.082. That means p is decreasing on the entire interval to the left of x equals 0.082. P is decreasing, then p flattens at the critical point. On the interval between the critical points, I'm going to pick an x value. I'm just going to pick x equals 1. Plug x equals 1 into the derivative. P prime of 1 is 31. I don't care that it's a value of 31. What I care about is that it is positive. P prime is positive on this entire interval between the two critical points. That tells me P is increasing on the entire interval between the two critical points. So right now we know P was decreasing, then P flattens, so it looks something like so, flattens at x equals 0.082, decreasing on the left, and increasing on the right. So right now, because the derivative changed sign at that critical point, I can conclude that this is a local min. There is a local min at x equals 0.082. Then at x equals 3.251, p of x flattens again. And now I'm going to go to the right of x equals 3.251. I'm going to test the derivative. So I'm going to just plug in x equals 4. If you plug 4 into the derivative, you get negative 44. I don't care that it's negative 44. What I care about is that it is negative. P prime is negative, which tells me P is decreasing on this entire interval to the right of x equals 3.251. So here's what we know about P of x. It's decreasing, then flattens at x equals 0.082, then increasing, then flattens at 3.251, then it's decreasing again. So roughly, it seems that P of x looks like this. There's a local min at x equals 0.082. There's a local max at x equals 3.251. And if you're sketching this out while you're making your conclusions, it seems to me that there's probably going to be an inflection point right in between these two. And that's our next step, is we're going to see if there is an inflection point, and I suspect we will find that it's between the 0.082 and the 3.251. All right, our next step then is to identify any inflection points on the graph of p of x. So here again is p of x, and its derivative we found was negative 15x squared plus 50x minus 4. To find inflection points is to find when the concavity changes. And remember, it is the second derivative that helps us identify concavity of p of x. So I need to find the second derivative, p double prime. So p double prime is the derivative of p prime. So here's p prime. We're going to find its derivative. It'll be negative 30x plus 50. Let me just make a note here about what I know. When p double prime is positive, p is concave up. When p double prime is negative, p is concave down. So if we can find the point where that change occurs, where p double prime changes from negative to positive or changes from positive to negative, that will tell us when p changes concavity. That will tell us the inflection point. So p double prime would change from positive to negative or change from negative to positive when it crosses through the x-axis. So when p double prime is equal to 0, or when p double prime is undefined, it could also make that sort of change. But p double prime here is just a linear function. It's never undefined, so we don't have to worry about that type. We're going to focus our attention on finding when p double prime is equal to 0. I set p double prime equal to 0. I solve the equation. So I add 30x on both sides, divide by 30. We get x is 5/3. That does not mean that you can now stop and conclude that this is an inflection point. Instead, what we know is that x equals 5/3 is a potential inflection point. To prove that it's an inflection point, we actually need to test the sign of p double prime on both sides of this x equal 5/3 value. So I'm going to draw a little number line. I'm going to put x equals 5/3 on my number line. And my question is, does p double prime change sign at this value? At this value, p double prime is 0. What is the sign of p double prime on the left? What is the sign of p double prime on the right? So I'm going to pick an x value to the left of it, like 0. Plug 0 into p double prime. Plug it into our p double prime function up here. If you plug 0 into p double prime, you'll get 50. That tells us p double prime is positive to the left of x equals 5/3. That tells me p is concave up. to the left of x equals 5/3. I'm going to do it again on the right side of x equals 5/3. I'm going to evaluate p double prime at, we'll say, 5. Any number to the right of x equals 5/3 will do, but I picked x equals 5. When I plug 5 into p double prime, I get negative 100. So anywhere to the right of 5/3, p double prime will be negative, which means anywhere to the right of 5/3, p will be concave down. So to the left of this x value, p is concave up. To the right of this x value, p is concave down. So I can now conclude x equals 5/3 is an inflection point because the concavity of p changed at that value. Overall, then, we can say p of x is concave up and then concave down. The change occurs at x equals 5/3. We'd previously determined that p of x has a local minimum at x equals 0.082, and p of x has a local maximum at x equals 3.25. So this is a nice rough sketch of p of x.